heavy to calculate. Right, so based on the convex hull again, these are the convex hulls of the two classes. If the intersection is empty, like in here, then there's an infinite number of planes that can separate class 1 from class 2. If the intersection is not empty, then we can conclude that the two classes are not linearly separate. Now, based on this convex hull, we developed a heuristic for computing linear separability. We actually perform the x minus y difference in here. We create a convex hull, and we know that if the center is not inside the convex hull, then the classes are linearly separable. If the origin is inside the convex hull, then the classes are not linearly separable. Now, those of you that know a bit about complexity, we know that it's a bit expensive to calculate the convex hull for n dimensions. And so, not only that, but finding whether the origin is inside the convex hull is also very expensive. So we came up with this approach heuristic that basically counts the number of quadrants, 1 to 4 quadrants in 2 dimensions, 6 in 3 dimensions, and so on. And we can estimate whether there are points in all the quadrants. If we have points in every quadrant in here, that means that the origin is in the middle. And we do not have to compute whether the origin is inside the convex hull. So very cheaply, we can find this heuristic that will tell us whether we have points in every single quadrant. That's the basis of the heuristic. I want to show you some estimations that we've done. This is with the time-wise. We decided to create 10 artificial data sets on 10 dimensions, and we then applied the quadrant, the convex hull, and the perceptron to find whether the classes were linearly separable or not. And you can see the times in here, which are far less significant with using the quadrant than it would be if you use the convex hull or the perceptron. The problem with the convex hull is the complexity of the calculation. The problem with the perceptron is not knowing beforehand whether the classes are separable or not. It's guaranteed to find a hyperplane if they are linearly separable. How do I know that in 10 dimensions? I don't. You have to sort of give it enough estimate or guesstimate, I would say, some number of times that it will go looking for the plane until we decide that the classes are not linearly separable. Okay, so briefly, I'll just introduce the RDP that uses the notion of linear separability within sets that are not linearly separable. So this is obviously essential to introduce and to know the existing method for testing linear separability. The more efficient these methods are, the quicker and efficient method will be. I've introduced some of the more commonly used methods for testing separability. So briefly, we have total linear equations, computational geometry, neural networks, support vector machines, and the estimated feature linear estimation method. And I've also introduced a brand new method for testing, which is the class of linear separability, and the use of the convex hull for a heuristic that looks into quadrants and finds very quickly whether two classes are not linearly separable. Okay, so with that in mind, now that we know about linear separability, we can actually move into the actual recursive deterministic perceptron. This is a multi-layered neural network. It is, as the name suggests, a generalization of the single-layer perceptron. The contrary to the perceptron is capable of solving non-linearly separable classification problems. It has automatic construction against, for instance, support vector machines, where it's got one with the right kernel, and it gets a bit complicated. There's no parameters to adjust in here. It does all the work. The convergence is guaranteed. If we look at other alternatives like backpropagation, well, we could take a local minima very easily and get stuck in there. We are guaranteed to converge with this method. One of the things that we have in here is also what we call catastrophic interference within the domain. This relates to the fact that if we look, for instance, at the fact that you speak Spanish and you learn English, it doesn't mean that because you learn English, you're going to lose your knowledge of Spanish, right? So this happens with backpropagation. If I train a neural network to forecast solar radiation here, if I want to move that neural network to, say, England, I'm going to have to retrain it because you wouldn't be able to say, okay, I know what it is in terms of solar radiation in Ecuador, but if I go to England, the conditions are not the same. So I need to, the only option is to retrain everything and have what we call the statistical pairs. With the RDT, you can carry on building from where you were. So it's kind of a big advantage. There is no learning parameters. If you go back to backpropagation, for instance, we have the learning rate of and depending on how low you go, you will be able to jump over the minima or the global minima, or you might get stuck in local minima. Another advantage that we have in here is in terms of knowledge extraction. A lot of people like to know how we found a relationship. But exactly, this is the solar radiation here, but I want to know why I'm getting that value. So explaining improves how we get the value is a bit difficult with networks like backprop, and it's transparent with the RTP. We find that although less precise backpropagation and cascade correlation and related chart success of backpropagation, our generalization is comparable, not as good as backpropagation, but close enough to the generalization that we obtained here. We've done some benchmarks and satellite images using the big technical techniques we are comparing. Okay, so the principles for building RDPs are very simple. We know by a fact, this is a fact from the convex poll, that for any non-linearly separable problem, there is at least one point, not more, which is linearly separable from the rest. Okay, that's the principle. So we go about selecting linearly separable subsets within a non-linearly separable set that will complete in a minute. And this is the way we go about building a neural network. We select that linearly separable subset. We add an extra dimension to the input vector. So we start with a two-dimensional problem, then becomes a three-dimensional problem with an intermediate perceptor that is separating that subset from the rest. We then mark this linearly separable subset that we already used, so that we only mention one. This is to avoid the guarantee of convergence of the. And we know that either we end up with no points left to play with, or we end up with a problem that has become linearly separate. So that is the guaranteed stopping condition of the algorithm. Just to illustrate, this is the typical XOR function, which as we know is not linearly separable. There is no single line that can separate reds and blues. So the way we built it is by looking at points or subsets which are linearly separable. So this red point in here is separable from the red. This red in here is also linearly separable from the red. So 1, 2, 3 points separable from these points. And so on with the other points is again the blue is separable with a line from the rest, and this point as well. So we look around points. As we go along, we probably, to help the algorithm converge quicker, we want to use the subsets which have maximum cardinality, meaning the subsets which are linearly separable and have the largest set of points indexed. This is quite complex as well. So for this example, we decided to take this point in here, and we're going to raise it up, building a normal perceptron, linear perceptron, which is going to classify that point 0, 0 as being of value 1, and the remaining point being of value 0, and this is done by here. Okay. We then list with that extra variable in here, gives the problem into 3 dimensions. And so we add a component, a third component, because we need input vector, 1 coming from here, 0 for all the others coming from here. And then we can only verify that with that structure in here, an original non-linearly separable problem has been transformed into a problem which is linearly separable. Okay, that is the principle of the. So with that in mind, we have developed 3 methods We have the batch, the incremental, and the modular.
So when we say NLS, non-linearly, we mean not linearly.
Yes, not linearly.
I mean, non-linear separable suggests that you can put a non-linear curve through it.
No, not
linear.
Not linear. So the modular approach obviously can be divided with a combination of modular batch and modular incremental. Okay, I'll explain a bit how this all works. So let's look at a dummy sample in here. We have cluttered them down to separate. Obviously, this is quite meshed. The two clusters are quite combined together. We go about selecting linearly separable subsets which belong to the same class and have maximum cardinality. Again, this is to help the conversion quickly. We add extra dimension for every subset that we separate from the rest. And the main problem we have in here is that this is an empty complete probe. Okay, and you probably have to remember that one of the materials is not the only method that we have available. So I quietly managed to steal some CPU from the French army. I never got to thank them because I was supposed to steal CPU from them, but a friend of mine kindly ran it over in the evenings to be able to cope with the complexity and to show that the method actually works with that range. The other method I will explain now came after my PhD. So basically what we do here is select chunks which are linearly separable. So we start with this subset in here which is linearly separable, this one in here, from all the rest of the points. We build one dimension to separate them from the rest. We then go about finding other chunks in 3 dimensions this time. It looks like this is the second set of dimensions. Then this is the high cardinality for the 4 dimensions, 5 dimensions, and clusters, and the 5th dimension, and we go up to 6 dimensions until the problem becomes linearly separable. So for an original 2-dimension subset, we have come up with 6 extra dimensions before the classes became linearly separable, and we end up with a topology that looks like that. Each of these is interconnected, and each of them represents a linear perceptron. Okay, so this is the sort of cascade that we have. Now the incremental method consists of training using only a subset of the training data set. And also we start with the data set that has the highest number of points. And then we add 1 point at a time for the remaining points. If a new point is well classified, we have anything to do. If it is misclassified, we need to add an extra dimension. Contrary to the previous method, this is the complexity of n again. You will always see the advantage of using this method. We started here with separability between A1 and B1, which are linearly separable, in here. We then went about adding point 1, which belongs actually to the other class, and is therefore not linearly separable. We need to add an extra dimension to accomplish all that. And we go on building the network, and we finish with a similar topology than the other method, except that the topology here, the complexity, much more better than the entity that we have in the batch. The modular basically is a divide and conquer approach. Consists of splitting the original problem into smaller problems, solving them because of them